Happy Tuesday. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are 3 different classes that may be observing the session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. So today, after we answer questions from 11.3, we'll be going on to section 11.4. But let's go ahead and get started with the questions from 11.3. And let's see here. First up, we have question number 14 from 11.3. It says a colony of 3 million bacteria were determined to be growing in the culture medium shown in illustration A. If the population P of the bacteria after T hours is given by the function P of T equals 3 million times 2.3 to the T power, find the population of the culture later in the day using the information given in illustration B. All right, well, first of all, let's take a look at our function here. P of T equals 3 million times 2.3 to the T power. They told us in the reading that it started with 3 million, but if you look at it, we could determine that anyway. At the beginning of the problem, T would be 0. If T is 0, 2.3 to the 0 power is 1. 1 times 3 million is 3 million. So at the start of this problem, the population of bacteria is 3 million. Now, looking down below, we see that at the beginning, it's 6 a.m. Oops, okay. Now, if we look at illustration B, it's 10 a.m., which is 4 hours later. And T stands for the number of hours. So what we need to do is find P of 4. So given that P of T equals 3 million times 2.3 to the T power, we need to find P of 4. One other thing I want to mention, notice that the base of the exponential part is 2.3, which is larger than 1. So this is a case of where a population is growing, okay? It's not decaying, it's growing. Okay, so now going to our other screen, we need to find P of 4, which would be 3 million times 2.3 to the 4th power. Putting that in our calculator, 3 million. Let's see if I got enough zeros there. 2.3 raised to the 4th power. And I come up with 8395230. So 83,952,300 would be the population of the bacteria 4 hours after the beginning of the problem. Any questions on that before we go on to the next problem? Okay, next up is number 17 from that same assignment. So let's take a look at that. It says the population of North Rivers is decreasing exponentially according to the formula P equals 3,745 times 0.93 to the T power. Notice something already. The base of our exponential part is less than 1, which explains why it's decreasing. Okay. T is measured in years from the present date. Find the population in 7 years, 3 months. All right, so T is time in years, and it says we want to go 7 years and 3 months into the future. Okay, 3 months would be 1/4 of a year, or 0.25. So we want to find P of 7.25. Now, this particular equation wasn't written as a function, but it is a function. So I'm going to just put it like this. And so we want P of 7.25, which is 3,745 times 0.93 to the 7.25 power. So 3745 times 0.93 to the 7.25 power. It says to round your answer to the nearest person. I'm getting 2,212.8. So we would round the 2 up because of the 8 in the 10th column. So 2,213 people would be the answer to number 17. Any questions on that before we go on? Okay. Let's take a look at number 21 off of this assignment set. And let's see here. It says, assume there are no deposits or withdrawals. If $1 had been invested on July 4th, 1776 at 5% interest compounded annually, what would it be worth July 4th, 2076? Round answers to the nearest cent. Okay, and I'm looking at this problem, and we'll go ahead and do it, but it looks to me like the student had the right numbers. I think the only thing that's wrong is there's a comma missing between the 3 and the 9. But let's go ahead and do the problem. So let's see here. We're going to use the formula A equals P times the quantity 1 plus R over K to the KT power. The principal is $1. The interest rate is 5% or 0.05. The number of compoundings is 1 per year, so that would be 1. The time would be 300 years. Okay, so we're going to look at the whiteboard screen. A equals 1 times 1 plus 0.05 over 1 to the 1 times 300 power, which is 1 times 1 plus 0.05 to the 300th power, which is 1 times 1.05 to the 300th power, which is 1.05 to the 300th power. Now, I would have to do this part before that, but I know that at the end, 1 times whatever is going to still be the whatever. So if I put that into my calculator, 1.05 to the 300th power, I get 2,273,996.129. Rounding to the nearest cent, the 2 rounds up, so 2,273,996.13. This is dollars, but again, we need a comma there and there. So I believe the only mistake there is the lack of the comma between the 3 and the 9 back in that original problem. Okay. Let's see here. We're going to look at some more questions. Okay. Let's see here. 11.3. Number 16. I know you can't see it yet. Just give me a minute. Okay. So we're still in section 11.3, and this is number 16. It says the charge remaining in a battery decreases as the battery discharges. The charge C in coulombs, boy, I've never heard of that, after T days is given by the formula C equals 3 times 10 to the negative 4th power times 0.7 to the T power. Find the charge after 9 days. Okay, so T is the number of days. So we want to put 9 in the place of T. So let's go back here. So C of 9 would be 3 times 10 to the negative 4th power times 0.7 times 9. Okay. So I've got 3 times 10 to the parentheses, negative 4, close parentheses, power, and then times 0.7 to the 9th power. Now, when I do that, I get 1.21060821 e negative 5. Okay, that's what shows up on my calculator. Now, let's see here. Interesting. Now, the reason I find this interesting is because in the assignment, it says round your answer to 9 decimal places, but I don't know if you can see they've got the correct answer here, and it doesn't take it out to 9 decimal places. So I'm kind of curious about that. But what I do want to talk about is the notation that your calculator might have. My calculator has this show up, in that E is basically 10 to some power. So this is like 1.210600821 times 10 to the negative 5th power, and that's in coulombs, or however you say that. Okay.
How did you enter it in the calculator?
Say that again.
How did you enter it in the calculator?
Okay, let me tell you here. I'll write it down. So let's see. Am I showing my white screen? I don't know if I am or not. So, okay. Here's what I did. I put 3 times, that little symbol is what shows up in my calculator as a times, 10 to the negative 4, close parentheses, power, times 0.7 to the 9th power equals. And when I did that, this is what showed up. Can you get that to work out okay?
It keeps on giving me a weird answer.
What is it giving you?
0.0000121106.
Okay. So do you remember what scientific notation is?
Yeah.
Where you use powers of 10. This answer is written in scientific notation. Your calculator is giving you an answer that's not in scientific notation. And there should be a button on your calculator that says mode up near the top left.
Okay.
Push that and choose from the menu, choose SCI.
Okay.
And then go back and then put that in and see if that works.
Oh yeah, I got it now.
Okay, now you're probably going to want to switch your calculator back to normal mode, because otherwise it's going to give you all your answers in scientific notation now.
Okay, thank you.
All right, we're going to take a look at number 17. And again, I'm not sure why this student asked for it, because the answer is correct, but maybe there were some issues. So we'll take a look. And so number 17, the population of North Rivers is decreasing. Now, is this the same numbers we had in the last problem? No, it's a different time. Okay, so we've got P equals 3,745 times 0.93 to the T power. T is measured in years, 5 years, 9 months. 9 months would be 3/4 of a year, or 0.75 years. So we need to find P of 5.75. Everybody okay with where I got the 0.75? So here we go. So now we're going to put this into our calculator. 3745 times 0.93 to the 5.75 power. And I'm getting 2467.33. And it's said to round to the nearest person. So 2467 people would be the correct answer for that one. Okay. Now let's see, we've got some more questions. And as I've always said before, if I start doing a problem that has the exact same numbers as a previous example, please let me know. I don't want to bore you to tears more than I have to. Let's see, okay. 11.3. Number 15. Okay, let's see, number 15. So this is also from 11.3. Problem number 15. 500 grams of a radioactive material decays according to the formula A equals 500 times 2/3 to the T power. I want to point out, it says it's decaying and our base is less than 1, so it would be decreasing or decaying, okay? Where T is measured in years, find the amount present in 12 years, round to the nearest 1/10 of a gram. So we want to find A of 12. Okay, because T is years and we want 12 years. So we're going to put this into our calculator. So 500 parentheses 2 divided by 3 close parentheses raised to the 12th power. And I'm getting 3.85. It said round to the nearest 10th, which would be in the 8 column. The 5 would round up. So 3.9 grams would be the final answer. Any questions about that one? Okay. Let's see here. We're going to take a look now at number 18. An initial deposit of $10,000 earns 16% interest. Wow, that's a great interest rate. Compounded quarterly, how much will be in the account after 10 years? Please give the answer to 2 decimal places, which basically is going to be rounding off to the nearest cent. So we're going to use the formula A equals P times the quantity, 1 plus R over K to the KT power. P is $10,000. R is 16% or 0.16. K is 4 and T is 10 years. Any questions about that? All right. So A equals $10,000 times 1 plus 0.16 over 4 to the 4 times 10 power. Now, in this case, things simplify nicely. So you could just put it in as it is, or you could simplify it. You know what? I'm going to just put it in as it is. And this is what I'm going to do. I'm going to put in 10,000 parentheses 1 plus 0.16 divided by 4, close parentheses, then the little caret for the power, parentheses 4 times 10, close parentheses, okay? So if I put that in like that, I can do it all at once without simplifying anything else further. I'm going to do that one first. 1 plus 0.16 divided by 4, close it up to the parentheses 4 times 10 power. And when I do that, I get 48010.206. The 6 would round up, so I'm going to get 48,010.21. So $48,010.21. Now, if I wanted to, I could take this and make it into 40, and I could take this and make it into 0.04, and then take this and make it into 1.04. So I could simplify those and then do that, and that should give me the same answer. Let's see if it does. And it does. But again, you don't want to simplify these things unless they still come out nicely. You don't want to round off ahead of time, okay? All right, that was 18. Now we're going to go back and take a look at number 19 in that same section. Let's see here. It says, assume that there are no deposits or withdrawals, an initial deposit of $12,000. So P is $12,000, earns 6% interest. So R is 6% or 0.06, compounded monthly. So K is 12. How much will be in the account after 12 years? So time is 12 years. Round your answer to the nearest cent. Okay, so basically the same kind of problem. So A equals $12,000 times 1 plus 0.06 over 12 raised to the 12 times 12 power. Well, let's see. 0.06 divided by, oops, you got to turn your calculator on first. 0.06 divided by 12 comes out nicely. You know what, I'm just going to do the whole thing like it is. So I'm going to go 12,000 parentheses 1 plus 0.06 divided by 12 close parentheses caret 12 times 12. Oh, whoops. So I'm going to have 12 times 12 in parentheses. Okay. So 1, 2, 0, 0, 0, parentheses 1 plus 0.06 divided by 12, close that up, raise to the parentheses 12 times 12, and I'm getting 24,609.009. This would round up. 24,609.01 would be your final answer. Now, you could change this to 144. You could change this to 0.005 and then 1.005 if you wanted to, because it comes out nicely, but you could do it either way. Okay, number 20 coming up here. If at any time you need me to stop or go back, please say so. Otherwise, I'll just keep cranking them out here. Assume that there are no deposits or withdrawals. Which institution in the illustration provides the better investment? A is 5.65 and B is 5.75. Now, one of them is compounded monthly and the other one is compounded annually. So it's like we're comparing apples and oranges, because you might look at A and B and say, well, B is a better interest rate. True, but A is compounded 12 times a year and B is only compounded once. So let's see how that's going to work out. Okay, so let's take a look at part A and part B. For A, oh, it doesn't tell us how much money we're investing, does it? Well, let's just pick a set amount. How about $1,000? Okay. So in both cases, the principal is $1,000. The interest rate for part A is, let's see here, 5.65%, which is 0.0565. For B, it's 5.75%, which is 0.0575. Okay. K for the first one is 12. For the second one is 1. And time, let's see. It doesn't really even tell us how much time, does it? Let's just make up some time. How about let's go 5 years. Okay, so let's see which has the better rate. Okay, or which is the better investment, same thing, better overall. Okay, so part A, I've got $1,000 times 1 plus 0.0565 over 12 raised to the 12 times 5 power. Okay, so when I do that, 1,000 parentheses 1 plus 0.0565 divided by 12, close it up, raised to the parentheses 12 times 5 power. I get 1325.562673. Okay, now let's do part B. This would be 1,000, 1 plus 0.0575 over 1 to the 1 times 5 power. And I get 1,000 parentheses 1 plus 0.0575 divided by 1 closed parentheses raised to the parentheses 1 times 5 power. And I get 1322518, etc., etc. So even though the first one had a lower interest rate, because it was compounded 12 times a year, it was slightly better than a higher interest rate compounded only once a year. All right, let's see here. Now we've got one more person's questions to look at. Let's see here. Okay. $16. Yes, here's that one again. And that looks like it might be the same problem. You can tell me here in a minute. I know we did this problem, but I don't know if the numbers were the same. Did we do this one with a 9?
Yes.
Okay, so that's going to be the same as a problem I did previously, so I'm going to skip that one. And let's take a look at 17. And 17, we also did, I don't know that we did 6 years, 3 months. 6 years, 3 months would be what, 6.25 years? So you're going to do P of 6.25 because 3 months is 1/4, 3/12, or 1/4 of a year, or 0.25. 3745, 0.93 to the 6.25 power. So let me look at that. We've got this situation. So on our calculator, 3745 times 0.93 raised to the 6.25 power, we get 2379.41 5304. Rounded to the nearest whole person, the 4 would round down. So 2,379 people. Okay. All right. So that takes care of the questions that people emailed me. Are there any other questions from anyone before we go on to the next section? All righty, and we shall go on. So let's get rid of that. And take it back to this screen. So now we're going to take a look at section 11.4. Okay, here we go. So if 2 to the 3rd power equals 8, and 2 to the 4th power equals 16, then 2 to what power? Pick a number between, a whole number between 8 and 16. Just pick a number. Don't be shy. Nobody wants to pick a number? Fine. How about 11? Okay. So if 2 to the third power equals 8 and 2 to the fourth power equals 16, 2 to the x power equals 11, what can you already tell me about x? Is there anything? Wouldn't it have to be larger than 3 and smaller than 4? Is anybody there?
Hello.
Thanks, Roger. I just thought maybe everybody went out to lunch. Okay.
Yeah,
Now,
maybe everyone else did.
that's okay. Thank you. Okay. At least somebody's still alive out there. All right. So can you see that x has to be between 3 and 4?
Yes.
Okay. Now, and we can sit down on our calculator and go 2.3 or 2 to the 3.1 power, 2 to the 3.2 power, et cetera, and eventually get an accurate answer or however far out we want to go. But there's got to be a better way. And there's something called a logarithm. If we take this equation, 2 to the x equals 11, and write it as a logarithmic equation, it looks like this. Log base 2 of 11 equals x. Now, especially if you've never seen this before, this is still kind of like, well, what do I do with that? But I do want to point this out. X is now isolated, okay? And during the course of this next few sections, we'll be looking at how to evaluate that expression on our calculators. So basically, putting something in logarithmic form allows us to isolate a variable that is an exponent, okay? So sometimes there's problems where the unknown is the exponent and we need to figure out what it is. So we take an exponential equation and write it in logarithmic form. Now, there's a simple way to change from one form to the other. The way that I like to describe it is using baseball, okay? And the way I describe it is like this. When an inning of baseball, you have 2 teams. One team is up to bat, the other team is out in the field, all right? And out in the field, there are 4 bases, home plate, first, second, third base are out there in the infield. When the players up to bat get 3 outs, the teams do what? They change places. Now, do the players out in the field, when it's their turn to go up to bat, do they go to the diamond and pick up all the bases and carry them into the dugout and the other team brings their bases out? You know, they talk about a stolen base. Is that what that is? No, the bases stay the same, but the players change places. Let me say that again. The bases stay the same, but the players change places. Now, let's say I've got this. Let's go back to 2 to the x equals 11. The base in this equation is 2. It's raised to the x power. If I write this in logarithmic form, it's log base 2 of 11 equals x. So here the base is 2, here the base is 2. The base is the same, but the players changed places. Here, the x is connected with a 2. Here, the 11 is connected with a 2. The bases stay the same. The players change places. Now, I want to point something else out, though. This is 2 to the x power. This is not 2 to the 11th power. It's log base 2 of 11 is how we say it. Okay, so let's use that idea in a bunch of examples here till you get comfortable with it. Hey, Nat, I'm in the middle of a Zoom meeting. I'll get back to you later. Thanks. Bye. One of my colleagues, I need to give him some information about upcoming classes. All right, moving on. Sorry. I guess I need to turn off my ringer. There we go. Let's say I've got this log base 3 of 81 equals 4. Okay, so what's the base?
3.
3. So 3 to the 4th power equals 81. The base is the same, but the players change places. You okay with that?
Yes.
All right. Log base 7 of 7 equals 1. What's the base?
7.
So 7 to the 1 power equals 7. In fact, let's do this even. I don't know if this will be helpful or not, but we'll see if it is. So you can see the red number is still the same number. Does that help at all? I don't know if it does or not, but okay. Log base 10 of 100 equals 2. So what's the base?
10.
So 10 to the 2 power equals 100. Okay with that? All right. How about log of 0.01 equals -2? Well, now here's a problem because there's no base written on that log. So mathematicians like to use shortcuts when something happens a lot. For instance, let's go back to when we talked about square roots or cube roots. The cube root of 8 is 2. The square root of 4 is 2. The index here is a 3. The index there is an implied 2. So if there's no index, it's the second root because that's the most common root. Well, one of the most common bases for logs is log base 10. So if there's no base written, if it just says log, that's the same as log base 10. And on your calculator, over on the left column, somewhere down there, there should be a button that says log, which is log base 10. And to help you remember that, if you look at the second function key, it's 10 to the x power. Okay, so log means log base 10. All right, how about this? X equals log base 9 of 81. So what's the base?
9.
So 9 to the x power equals 81. You okay with that?
Yeah.
All right, let's go the other direction. Let's say we've got 10 cubed equals 1,000. What's the base?
10.
So log base 10 of 1,000 equals 3. Or we could just say the log of 1,000 equals 3. And base 10 is referred to as common log because it's one of the most commonly used bases. Okay, so log of 1,000 equals 3. How about this one? 1/3 to the -3 power equals 27. What's the base?
One-third.
Okay, so log base 1/3 of 27 equals -3. Okay, any questions on that?
Nope.
Now, let's say we've got this equation, log base x of 9 equals 2. It says solve for x. It's not foolproof, but it's darn close that if you've got a logarithmic equation and you're trying to solve it, you put it in exponential form. And if it's an exponential equation that you're trying to solve, you put it in logarithmic form. Not always, but a good deal of the time, especially in this case. Okay, so log base x of 9 equals 2. If I rewrite that in exponential form, that'll be x squared equals 9. Okay. Now, let's see here. How would I go about solving this thing? Well, let's go back 2 chapters ago where we took the square root of both sides. So x is plus or minus 3. Do you remember doing that back in chapter 9? However, this is not correct. Now, there's nothing wrong with the process we did, but what we need to do is let's go back to yesterday when we talked about exponential equations. And we said, let's see here, y equals b to the x. We said that b can't equal 1. And we said that the domain was what? All real numbers. And the range was greater than 0. Do you remember that? Because like you get a drawing like this or like that. Okay, so and the base has to be greater than 0. And if the base is between 0 and 1, it decreases. Greater than 1, it increases. If you don't remember that, go back and look at your notes from yesterday. Well, the point I'm trying to make is this. If I take y equals b to the x and I change it into a logarithmic equation, it's log base b of x equals y. Okay, now b can't equal 1 and b has to be greater than 0, right? Those were restrictions that we talked about yesterday. But this b is the same as this b, which means b can't equal 1 and b has to be greater than 0. Oh, look here. Whoops. That can't be 1 and it has to be greater than 0. Therefore, it's just going to be the positive 3. You can't have log base a negative number because of the restrictions that apply. So watch out for that. Okay. How about this? Log base 27 of x equals negative 1/3. Solve for x. So writing this in exponential form, 27 to the negative 1/3 power equals x. But that would be 1 over 27 to the positive 1/3 power equals x, which would be 1 over, what's the cube root of 27? It's 3. So x equals 1/3. All right. Let's see here. How about this? Log base 3 of 9. It says evaluate each logarithmic expression. Log base 3 of 9 equals what? We'll tell you what, let's let it equal, let's just make it some box. So our answer is going to go in the box. Okay. Well, if I took this logarithmic equation and wrote it as an exponential equation, it would be 3 to the box equals 9. What if I took 9 and wrote it as 3 squared? Well, if the bases are the same, the exponents are the same. So that means the box is what?
Two.
Good. If the bases are the same, the exponents are the same. So log base 3 of 9 equals 2 because 3 squared equals 9. How about this one? Log base 1/3 of 1 over 81 equals 4. So this would become 1/3 to the 4th power equals 1 over 81. Oh, wait a second. Oh, sorry. I looked at the problem and it has the answer written next to it. And so I just wrote it down. We're not supposed to have the answer yet. That explains. I'm going, wait a minute. We didn't do anything there. My bad. Okay. Well, now everybody knows the answer. Okay, so we've got that. Log base 1/3 of 1 over 81 equals box. So that means 1/3 to the box power equals 1 over 81. Okay, but couldn't I write 1 over 81 as 1 over 81 is 3 to the 4th power, isn't it? Okay. Well, let's see here. What's 1 to the 4th power? Is that equal to 1? Does 1 times 1 times 1 times 1 equal 1? Nobody wants to make a stab at it? Okay, well, yes, it does. So this is like 1/3 to the 4th power. So what's the box equal?
4.
4. All right, now we're going to use our calculators. So we're going to use that button that says LOG. It says, use a calculator to find the value, give answers to 4 decimal places. So we've got log of 0.57, which is log base 10. So you're going to turn your calculator on, clear it. You're going to push the log button. On my calculator, when I do that, it comes up like this. Then I'm going to put in 0.57, close the parentheses, equals. So 0.57, close the parentheses, and I get negative 0.244125, etc. It said round to 4 decimal places, which would be the 1. The 2 would round down, so negative 0.2441 would be the correct answer. You okay with that? All right, one more example. This says log base 10 of x equals 2.8945. Well, I can't put log of x in my calculator, at least not effectively. But isn't this the same thing as log base 10 of x? So I could rewrite this as 10 to the 2.8945 power equals x. So now in my calculator, there's 2 ways I can do this. I can punch in 10, the little caret key, and then 2.8945 equals, okay, 10 to the 2.8945 power. And I get 784.33211, again to the 4th decimal place, so that would round down 784.3321. Or I can use that second function key of the log, the one that's the 10 to the x button. So I go second function, 10 to the x, and when I do that and I push that button, I get this showing up. And then 2.8945, close it up, you get the same answer. So it's really the same number of keystrokes, because here you've got to push 10 and then this power button and then put in the exponent. If you use the 10 to the x, you have to go second 10 to the x. So, you know, I'm not sure that it saves any time. Either way seems to work just fine. All right. So for tonight, 11.4, I will be back at 1:15. Should you have any questions? Otherwise, I will see you tomorrow. Have a great rest of the day. And that's all.